We have 1 over C5. I made C7 1 over C5.
Just giving a number.
I'll just rename it.
Okay.
But is that just fine? Okay. 1 over C5 is that. Then 1 over C5 is that. Plus C4 is parallel with that. Plus C2 is parallel with that. So that's this whole entire section. Then you can redraw it. And then these two are here. This is C6. And then those are in parallel. Add those together to make 1. And then it's in series with the crazy capacities that you did before. C6 was 1. Well, is it? Oh, I mean, that becomes no, but there's so you add these. So
Yes, you have to.
So 6, and then it's 1 over, then it's 1 over 6. Plus, then it's 1 over 6. Plus 1 over. What is it?
And then you can
If you're stuck, find somebody to talk to.
Oh no, that's 3.
I got it. Well, because if you're doing this parallel,
This is all 6. This whole thing is 6. Oh, it's under. Yeah. Cool.
she got it.
Yeah, but we did it together, so
Yeah, that's true.
our both threes don't have double values. They have the value of 1 and 3.
Give you a couple more minutes.
Wait, you just hit C.
We should figure out what I got 2
What did they get?
I got 2.
Oh, us too.
So first I did 5 and 3. They're serious.
Okay. So let's talk our way through this.
Yeah, okay. Yeah.
first task at hand is to simplify that 6-capacitor array to get it apparently down to a single equivalent capacitance. So, again, you're going to want to start out where these are obviously all in series or obviously all in parallel, which usually means starting in sort of small scale interior of a circuit like this. What's your inclination for the first thing you want to do to simplify this?
3 and 5 is in series.
Yep, so I would say 3 and 5 in series. So they are in series, so 1 over C35 equals 1 over C3 plus 1 over C5. Okay, we can put in numerical values if we wish, or we can algebraically, go ahead.
4 and 6.
Yeah, so I don't know if I have time to do this, but what you might do the first time through an exercise like this if you're having difficulty is redraw it at each step where you combine whatever you've combined and simplify that part of the circuit, okay? So I don't have time in this instance, but I will just replace C3 and C5 by something that I'm labeling C35, okay? So that would be my step 1. Okay, step 2.
So you see that C4 and C6 are also in series.
Okay, interesting. So C4 and C6 are also in series. They are, but there's something else between C4 and C6. Namely, there's a sort of junction in the circuit, okay? So it's not as though they're straightforwardly in series with nothing between those two components. In fact, there's a rather complicated remainder of the circuit that connects at that point. So this is a first sort of point where you have to be careful. This only applies if I really have only one way to pass through this. And that's not true if I look at C4-6 in the sense that I could take a step off halfway through, and I could go elsewhere through this circuit. So what you want to be doing when you're doing this exercise is to make sure that the parts of the circuit you're trying to simplify don't have any other junctions with other parts of the circuits in there. Okay. Okay, I like that. So remember now C3 and C5 have now become a single capacitor. So you said you want to combine C4 with that. That's a good start. Is there even more that we can add to that part of the circuit? Ariel. C2, yes. So I drew this in a way that was kind of particularly intended to throw your eye off. But if you look at C4, the combination of C3 and C5 and C2, they could be redrawn in a way that looks really quite similar to this. Okay? So there are, in fact, those 3 capacitors that could be combined together in parallel. So I would, for my second step, be inclined to say that, what is this, 2, 3, 4, 5. I would say that C2, 3, 4, 5, these are in parallel. So in this case, I have a straight summation. C4 plus C35 plus C2 would be my next step. Okay? So you can start to see this is not trivial always. Now think about this in your mind's eye, or draw it if you need to. I've now replaced all of those 4 capacitors up top by an equivalent single capacitance. And I will draw this, at least in the exercises when I first do this. So imagine that now as being a single capacitance and looking at what the circuit looks like next. What might be your next natural thing to simplify? Eli.
Combine C1 and C6 into one capacitor.
C1 and C6?
Into one capacitor.
Yep. And can you tell me, are they in series or in parallel with each other?
Parallel.
Okay. Good. So C1 and C6, maybe I'll pull this down quickly and try to manage enough time. Always my problem. I could imagine a finger here, or a finger here. My question is, how many sort of ways can I get from here to here? Not going through the battery. I can go that way, I can go that way, therefore they are in parallel. So I would be inclined to do C1, 6 like this. again in your mind's eye, think about what this looks like now. I've got C1, C6 combined in a single capacitor. I've got C2, 3, 4, 5 combined in a single capacitor. What does it look like at that point? Michael?
2 in series.
2 in series. So I'm doing a summation. Hold on. Wrong way around. Thank you. You guys were way too quiet then. These are indeed in parallel. So I need C16, C1 plus C6. And then what am I left with? I've got 2 in series, so I would have in this case 1 over, here's the full equivalent capacitance. I didn't write equivalent here, but I want to write it explicitly as comprising all 6. So now it is 1 over C2, 3, 4, 5 plus 1 over C1, C6. And I can plug and chug and get all of this. It turns out numerically, if I'm remembering correctly, that this becomes actually 3 microfarads. Okay, I'm a bit out of time, bear with me just a moment. I want you to read my solution to the remainder of this problem. But before doing that, let's just see what we would need to do as the next step. So part 2 here, what is the charge on the equivalent capacitance, will be fairly straightforward, right? Because at this point I know the capacitance and I know the V. So I can simply figure this out as Q equals C1, 2, 3, 4, 5, 6 times V. This is C1, 2, 3, 4, 5, 6. Okay, just as a introduction to going back and figuring this out. If I wanted you to tell me what is the potential across C1, how would you go back and start digging out the individual details? Jesse?
I would look at C2, 3, 4, 5, C1, 6, and see how they split.
Yep.
They must have the same charge when they're in the series together.
Correct. So if you want to say that again a little bit louder so everyone can hear it.
C1, C2, 3, 4, 5, and C1, 6, when they're in series, they have the same charge. So then you can find the ratio of their voltages.
Good. So look at these. They must have the same Q on them because they're 2 effective capacitances in series, the way we talked about over there. And in fact, that's the charge on the total equivalent capacitance. And then you would look at the Q equals CV relationship to find out what the delta V's are. So this would get me V16 and V2, 3, 4, 5. Now remember, these are now things that are in parallel within their sort of subunits. So if I knew V16, what could I say then about the voltage across C1? It's the same, right? I must have the same voltage drop across all capacitors in parallel. So what you're going to be doing in an exercise like this is once you've simplified it, you're going to go back and use these behaviors, these relationships, to figure out what the Q's and V's are in each of the components, okay? So it's a little bit tedious, but once you've done it a couple of times, it'll be great. Okay, let's stop there. Reminders, no office hours today, regular time tomorrow.
Get myself some snack.
Tuesday, 1, 2, 4 for me. Next day.
Time to eat lunchtime.
Time to do my chem lab. Ew.
Yeah, what are you, studious? First shame. First shame. Wait. Going this way.
No, because they're not kind of, it's not that this plate is only connected directly to this. What's driving it is the fact that there are so the important thing here is that these are kind of isolated, I mean, they really are. There's nothing connecting this. I can't have any effect, for example, on direct effect. The only way it can happen is if I induce the side buttons. What's different in this case is that I have a delta V on the outside.
So for example, if we don't have the power supply, all the charge can redistribute.
Okay, well if there were really no kind of like there's there at all, there's not going to be any charge anywhere. It's going to be so the reason that this asymmetry appears is because of the this way this asymmetry appears. So if this were not here, I would never have any
discharge capacity. Say for example, we have plasma charge, like no charge and very just reaction. So all the charge
It will redistribute, yeah, and we'll talk a little bit about what that means. I mean, if let's say, how would it get there? It doesn't really make sense. I mean, let's say you just put positive on here, and you put negative on here, which is isolated. So what you would expect in this case is that you would get a charge distribution depending on what your values are, still that you have the same delta V acoustic. You must have the same delta V. But it does mean you have to calculate what the Q's are depending on what the C's are. So you can use this again. So in this case, this would be constant, and then I'll take the charge to inverse.